Welcome back, everyone. So for our second talk today, we have Nikolay Konovalov from the University of Chicago, who will tell us about algebraic Goodwillie spectral sequence.
Thank you, Fred, for the invitation. Yes, so I'm going to talk about algebraic Goodwillie spectral sequence. And at first, I was giving this talk several times in different places. So if you already heard it before, then probably I wouldn't learn anything new from this one. Okay, so let me start with the following ultimate goal. So the ultimate goal is to compute the multiple groups, unstable multiple groups of some space X. For example, X is a sphere of dimension L+1, where L is some non-negative number. Of course, we know the answer when X is a circle and L equals to 0, but in general, this is a hard question. And this is the main motivation for it, for me. It's interesting because it's challenging. And just to illustrate how hard it is, I will say two theorems. One of them is due to Curtis, which says that unstable multiple groups of S4 are all non-trivial for the stem greater or equal than 4. And like I remarked, you actually can say the same for two-dimensional sphere. But it's a little bit harder to say who proved it first. This result was proven probably by Brendan Gray and Martin Bendersky, also proved recently by Fu, Ivanov, and Mikhailov. So as you can see, even for spheres, you've got some non-trivial sequence of finely generated apparent groups, and which might seem chaotic, but sometimes you see some patterns. Yeah, from Niesendorfer says about the torsion exponent for torsion in odd-dimensional spheres, in multiple groups of four-dimensional spheres, is bounded by N. So you have pretty nice qualitative result, but you don't see a torsion of exponent greater than b in the power of n. Okay, and one more warning during this talk, I will be talking mostly about multiple groups of odd-dimensional spheres, and all multiple groups will be completed at certain time. Okay. And now I'm ready to draw a main diagram for my talk. So I want to compute the multiple groups of one-dimensional sphere. Okay, so there are several computational tools for that. One of them is a Goodwillie spectral sequence, which takes as an input stable multiple groups of certain spectra, both D, H, evaluated on the sphere. Yeah, and this is a pretty nice spectral sequence, at least from the conceptual point of view, because it starts with a stable multiple groups, which is perhaps more tractable, and computes unstable multiple groups, which is more mysterious. On the other hand, you can consider another spectral sequence. You can consider unstable Adams spectral sequence as well, which, well, traditionally people started with the second page, which is certain X groups. But for spheres on general point space, you can start it with a first page. You can start with one, which is some complex called lambda L, subcomplex in the famous lambda algebra. Okay. But now, why not to let's not to start on two spectral sequences. We can consider more in this picture. In particular, when you work with a Goodwillie one, you want somehow to compute with the multiple groups first, which is not clear how to do. And for doing that, you can start with random spectral sequences for each of these spectra. When you do it, you got again with random spectral sequence. Again, you can start with the second page, but let me start it with the first one. The first one would use as input the homology groups of the given spectrum tensor on the lambda algebra L. Right, and now in the picture you see three spectral sequences, and you might ask, do you have some sort of spectral sequence between the first pages, some sort of Adams Goodwillie spectral sequence? Well, at this moment I don't want to specify what exactly do I want from that, but basically I want at the end I want to compute differential in Goodwillie spectral sequence by lifting them onto as a differential in some algebraic data. Okay, so this is kind of the problem, and this is the main diagram. Everything else would be not so important. Everything else would mostly my reflections about these four spectral sequences. Okay, but before that, let me recall a few properties for the Goodwillie one. So, what is the Goodwillie spectral sequences for who's who? So, Goodwillie constructed functorial tower of vibrations. So if you consider the identity functor from the category of spaces to spaces, and you consider the polynomial approximation of this identity functor, and when you evaluate this polynomial approximation on the given space X, you got a functorial tower of vibrations. With fiber, which is usually denoted Dn of X. This star satisfy two properties. Well, first of all, the original space X maps to the whole tower, and you can compare it with the homotopy limit. So this map is an equivalence. If X is simply connected, or X is a circle. More generally, you can say that it's equivalence when X is important, or even more generally, if it's HT local. But I'm not going to go such deep. And another nice property, well, another important property, was the layers of the star are infinite loop spaces. Which depends only on the suspension spectra of X. So, example. The first layer, the first approximation is simply omega infinity sigma infinity of x, and the Van der Waals D is an identity of the category spectrum. Well, in general, you got what the n of some spectrum y is a has a following form. So you can take a spectrum y, you can take its nth tensor power, you can tensor it with a certain spectrum delta n with a sigma n action, and you can take sigma precaution. In general, we can say that this function overall as follows. Delta n is a finite sigma n CW complex. Non-equivalently, it's just a bunch of spheres. Equivalently, and so it looks pretty simple, but equivalently it's more complicated. I don't want to give a honest construction or honest theorem about it. The only thing which I just want to mention is what if you take the homology of the spectrum, the homology of the spectrum, and the relevant part is only n-1, you basically return the nth space in the Lie operator. Maybe shifted by some by sign representation sort of power, but I just don't want to write it up. I'm sorry, any questions so far? Okay. And now one more theorem due to Aron and Mahomet. So this was star for general x, but for spheres it simplifies a little bit. So for spheres, when you take the spectra and take its with power, when it's trivial if n is not a power of p. So here I use the same the convention on p is odd when I consider only one-dimensional spheres, because even-dimensional spheres for prime are not so interesting. Okay, and so it allows me now to consider. So it means that most of these layers in this tower are trivial. So it's kind of a exponentially sparse. You can consider the spectral sequence for a sphere, which is just multiple groups, stable, all the spectra. Indexed by power of p, and which converges to unstable multiple groups of the same sphere. An example here is when L is equal to 0. So in this case, the spectral sequence is supposed to compute unstable multiple groups of a circle, which is, I guess everybody knows what is unstable multiple groups of a circle. However, the input data in this case is quite large. So trivial. It's trivial, but let's say let's say the zero row in the spectral sequence are unstable multiple groups of a sphere spectrum shifted by L, which is highly non-trivial. In other words, you got a spectral sequence which takes something highly non-trivial and converges to something trivial. And you would expect, you might expect some convoluted structure in this process. Quite surprisingly, it doesn't happen. So, theorem by Mark Berens and Nick Kuhn states that with spectral sequence for a circle degenerates at the second term. So you only see differentials on the first page, or everything will so any elements either supports the non-trivial differentials on the first page or killed by a non-trivial differential on the first page. So for a circle with spectral sequences is quite efficient, as you can see. And a couple of remarks about this theorem. So let me say that proof is not super conceptual, is not conceptual, is not conceptual. It's not entirely computational because, of course, you cannot compute the spectral sequence entirely, but you don't see from the proof why the circle is important here. Why namely the circle is what properties of the circle you use to prove it. The second remark is that this theorem is only a half of the actual statement. This is simple cycles. Form. So White conjecture. So the White conjecture is a kind of also a statement about degeneracy, about degenerations of a different spectral sequence, which happens to have the same terms, but the differential goes in another direction. And the statement that differential in Goodwillie spectral sequence and the differentials in the complex in differential in the complex for Whitehead conjecture give you contraction homotopies to each other. The next part is what it doesn't hold for high-dimensional spheres. So for high-dimensional spheres, you might have differentials on the second page or in some other pages, but still not so, surprisingly not so much. So in total range, GSS is still efficient. Meaning that you only see differentials in total range. You see differentials only for two-dimensional sphere, and you see only two of them on the second page. After that, it degenerate again. Okay. And probably the last remark. So the first differential here is related to James Hope invariant, which might be a little bit complicated, but if you put certain filtration on homotopy groups in the picture, then you can say what as a leading term for a certain filtration. is given by stable, unfortunately stable, covariant. Okay. So what was the story about Goodwillie's spectral sequence? But now let me briefly recall about other spectral sequences. What happens here? So let me say quickly what lambda is the Cauchy-dual algebra for the stimulant algebra. In particular, means that it's generated by some elements which are Cauchy-dual to the standard generators in the stimulant algebra. Since stimulant algebra is not quadratic, but is not homogeneously quadratic, but has some linear terms. Lambda algebra would have a differential, and the homology of this lambda algebra with respect to this differential are the X groups over the stimulant algebra from trivial model to the trivial model. And interesting moment about this lambda algebra is a totally algebraic definition. You can use it to compute the second page of the Adams spectral sequence, but you actually can construct a filtration on a given spectrum of a space, such that the first page with respect of the corresponding spectral sequence would give you a lambda algebra. So theorem by spectrum when there exists spectral sequence which takes the homology phi, tensors the lambda algebra, and converges to stable multiple groups of phi. And this spectral sequence coincides with the standard Adams spectral sequence starting the second page. So this theorem is due to six authors' paper. The theorem due to only two, which I will attribute only to two people in the six author papers, is that there exists subcomplex L. Subcomplex and spectral sequence which starts with this subcomplex and converges to unstable multiple groups over sphere. So yeah, so this is kind of the story. So like this, to this computational tool, some lambda algebra, and so on. Interesting moment about this lambda algebra is that this lambda algebra itself can be explained as a homotopy groups in the certain category, which is probably you can say the same about X groups or unstable X groups over the stimulant algebra. As a corresponding category, it would be more complicated case. For lambda algebra, it seems to be much more easier to describe. So, yes, all distributed algebras. So, in definition, so a restricted Lie algebra is a pair of Lie algebra over a field of characteristic P and some map from L to L. So this is Lie algebra. This is some map Psi. Such that, well, it satisfied a few properties. I just have to list them, but I will give in examples. It will be much more clear what happens here. So, and the last property, so this Psi is not additive, but you can say the arrow, and I don't want to say the actual definition. So some terms expressed in only in Lie brackets. So the main example here is the following. So suppose you have an associative algebra over a field of characteristic P. When you can construct, you can use the commutator bracket to give you a Lie algebra from the commutator. Give you a Lie algebra in bracket. But since you in characteristic P, you can consider also an operation which takes an element to its fifth power. And these two operations, the Lie bracket, the commutator bracket, and the taking the fifth power, will give you something like this restricted Lie algebra structure. You can say that if you take the commutator bracket with the fifth power, you can express it as a bracket with p times, and you can say that the fifth power of x plus y would be x in the power of p, y plus in the power of p, plus, since algebra is not commutative, some terms which can be also expressed in terms of the commutators of x and y. And this definition is basically to axiomatize these properties. A little bit more tricky example is what if you start with a commutative Hopf algebra. When the set of primitive elements is closed with respect to commutator bracket, which is always true, and also it's closed with respect to fifth power of taking fifth power of this element. Fifth power is primitive elements, again primitive. So when set of primitive elements is forms the restricted Lie algebra. And moreover, by Milner-Moore, I'm not sure, but this is what people call Milner-Moore theorem, but at least it's in the white paper. Any restricted Lie algebra has this power. So an irreducible algebra is a primitive element in a certain co-commutative Hopf algebra. And the last example is how the free restricted algebra looks like. So so for that, we need to take primitive elements in some co-commutative Hopf algebra. Let's consider the tensor algebra on vector space V. So the tensor algebra on the vector space V, it has a natural co-commutative Hopf algebra structure. And the primitive, and you can take primitive elements. This is going to be, you can check what this is a free restricted algebra. And as a vector space, it has the following form. So you take the operand, you can take a tensor product with the nth tensor power of vector space V. And afterwards, you take invariance with respect to the symmetric group action. If you would take co-invariance, you will get just a Lie algebra, free Lie algebra. But here I'm taking co-invariance and I'm taking, but here I'm taking invariance, which is something bigger. I'm taking co-invariance. And characteristic P, of course, and characteristic 0 it wouldn't matter. All right. Now the main category to construct my to talk about the algebraic Goodwillie spectral sequence is the category SN, which is a infinity category of simplicial restricted Lie algebras. Simplicial. So it's a simplicial objects in the category of restricted Lie algebras. Why it's relevant here? So here, it's again a bit about Smith and Curtis. So if you start with a simplicial vector space over a field, let's say Fp, then stable the multiple groups of the free restricted Lie algebra, which is by definition like this one, is precisely well, multiple groups of the simplicial vector space tensors the lambda algebra. So you can think about lambda algebra as stable multiple groups in the category of simplicial restricted Lie algebras. And another property is what if you start with just one-dimensional vector space concentrated in degree, simplicial vector space concentrated in logical degree L, when unstable multiple groups of the free simplicial restricted algebra is just a set complex lambda L inside lambda. So in this mode, in this word of simplicial Lie algebras, unstable multiple groups of free object embeds into stable multiple groups. Yeah. So and for the second part, I choose V to be one-dimensional only because for V of higher dimensions, the answer is a little bit more complicated. I don't want to spend right now. Okay. And now, so now I'm ready to give the answer what it's supposed to be here, what it's supposed to be with algebraic Goodwillie spectral. So let's consider the functor of over free simplicial eCHT algebra. So this functor takes simplicial vector spaces and give me a simplicial eCHT algebra. So it's a functor from this modes category to simplicial eCHT algebras, and both categories on the left and the right are good enough to apply the Goodwillie machine, to apply the functor calculus. If I apply the functor calculus, I again get tau of vibration. Fibers. Okay, so I have standard vibration, and what I can say about the fibers. So position, which is basically falls on the Moore theorem. Let's say it's me. So the fibers in the star, when you relate on some space beam, has the following one. So you take B, you take its tensor power, and you tensor it with M space in the Lie algebra, and now take the homotopy in coinvariance. Afterward, apply a free functor and use standard adjunction between the category and its stabilization. So this is a stabilization. Right. So and the end is again it's a kind of space in the element. Okay. So now okay, so the proof goes through the computation of cross effects and basically boils down to the Hilton-Milner form theorem. And one more remark about this stabilization, that this stabilization is quite a non-trivial category. I do not have any different description for that, unfortunately. Okay. But now this proposition has two columns. So if is just one-dimensional vector space, it's situated in homological degree L, when these layers are contractible, if n is not a power of p. This is again due to Roland-Mahold, because this space here are precisely the homology of the topological layers, precisely the homology of this space. So one color, and more generally, if you try to compute the homotopy groups of the layers, then this is the same as the homology of the fibers. It's a topological Goodwillie tower. Sorry. evaluated for a sphere of dimensional +1. Then there's the lambda algebra. And second corollary. So now we have a tower vibration, which again converges to the free object. And the second corollary says that you got algebraic Goodwillie spectral sequence. Whose first term, well, it depends on the vector space, whose first term happens to be the homology of topological layers, that's the lambda algebra, and it converges to unstable homotopy groups of the free simplicially restricted Lie algebra generated by this vector space. But this is so it's converges to not just to this guy, but we know what this guy is the same as a subcomplex lambda L. So we got precisely the spectral sequence of the formulas here. Its first page homology of the topological layers, tensors the lambda algebra, and then converges to the subcomplex lambda L. So now I probably have time for one more statement. Theorem, kind of a generalization of the theorem of Barons and Kuhn, but with algebraic Goodwillie spectral sequence, well, evaluated. Yeah, degenerates on the second page for all L greater or equal than 0. So once again, we have some degeneration, the same degeneracy as in Barons and Kuhn theorem, but now we see we have much more examples, spaces of objects where this generations happens. So at least having more examples might be more useful to shed some light why this theorem actually holds. Unfortunately, even for this algebraic theorem, this is a computational one, because and now it's purely computational because we actually can compute the whole spectral sequence. And we know how the lambda algebra looks like, we know how the homology groups for the spectral looks like. We can describe them in terms of the certain homology operations. And basically, with some work, maybe a lot of work, you can describe the whole differentials explicitly. You can show what with the generations happens. Okay, so I think I have to stop at this point.